Thank you very much for the kind introduction, and I'm very glad to be here today with all of you. And I'm very happy and thankful for the big opportunity to share with you the work we are doing in our laboratory. I will use the pointer. So our laboratory is located in Granada, that is in the south of Spain. We are in the School of Sciences of the University of Granada. That is a big science school where many degrees are taught in the same building. So it's a very rich environment for collaborative research with other fields and interdisciplinary research, because we have biologists, chemists, engineers around, so that we try to perform we try to take advantage of this environment by interacting with all these researchers that are around us. So you have here a nice picture of the lab. Back here you can see the NanoTracker device that I will be discussing today mostly about. And yeah, so as I already said, we do multidisciplinary research. So we do research on different lines. For example, the first one is this what we call non-equilibrium process with single and multiple trap particles, so that we use trapping techniques to, let me activate this video, to trap with our optical tweezers particles and drive them out of equilibrium, either by using single particles, like you see here in the tweezers, or with other devices we can also trap multiple particles or force aggregation in the presence of a laser beam, or even work with levitated particles. Let me see if this video works. But back down here, these are levitated particles that are trapped in a pole trap at ambient pressure. And they are compressed and expanded by changing an external electric field. We also have our optical tweezers device combined with a Raman spectroscopy device, so that we are lately using it to measure the surface-enhanced Raman spectroscopy of molecules of interest, like dopamine, for example. We also study aerosols, like optical properties of aerosols. So down here, you see there is a small particle that scatters light, and it is levitated by an electromagnetic field. And by looking at the interference fringes that are created when a laser is shining on them, we can extract information about the optical properties of droplets, for example, that are levitated in a pole trap at ambient pressure. And finally, we also combine lasers, laser light, with electric fields. Sorry, this video doesn't work. Sorry, this video doesn't work. Okay, but we also combine electric fields and the lasers from the tweezers to get enhanced manipulation capabilities, as I will show you later. Okay, so most of the discussion I will share with you today is about particle trapping. And we usually describe a particle that is trapped as a Brownian particle that executes Brownian motion when dispersed in a fluid or in air. And a free diffusing particle will behave like this one, but with a different mechanism. One can develop a parabolic potential like this one that confines the particle to a very small region of space. The origin of this potential can be different. We will focus today on optical tweezers, so that this potential will be created by a laser beam. But there are other techniques that I will also discuss that are able to create such a trap. In simple terms, we can describe a particle in a trap like a Brownian harmonic oscillator. And as a first approximation, one can describe the particle in the trap as a mass in a spring system, where the force that the spring exerts on the particle is proportional to displacement, and the constant of proportionality is what we call the stiffness of the trap. The description in terms of the motion of the particle can be done in terms of the overdamped Langevin equation. That includes a friction term, so that there is some friction force when the particle moves because of the viscosity of the particle, so that this gamma is the Stokes friction coefficient that is proportional to the viscosity of the liquid and to the size of the particle, as you see here for a spherical particle. And then we have a force term that is the force executed by or applied by the spring. In our case will be the optical tweezers. And we have to include in this equation the Brownian motion that is typically modeled as a white noise with intensity that is proportional to the temperature of the environment, of the system, or of the medium where the particle is dispersed. One way to create such a trap is by optical tweezers, and well, that is why we are here today. Arthur Ashkin developed this technique whereby tightly focusing typically an infrared or a visible light laser beam, with a high numerical aperture objective, you can create a force acting on a dielectric particle that is typically proportional to the gradient of intensity. That's why you need very strong focusing, so that to have stronger intensity gradient. And this force is restoring in all three directions of space, so that the particle is typically pushed to the focus of the laser beam. If the particle has, has a refractive index, or the material the particle is made of has a refractive index that is larger than that of the medium. So typically for dielectric particles, you will experience a force that is proportional to the gradient of intensity by this factor that is usually called the Clausius-Musotti factor. The technique is very versatile in terms of applying different forces that are proportional to the laser power, so that you can finely tune the force or the stiffness of the trap, and by that the force you are applying on the trap particle. And also you can take advantage of the laser beam, of the part of the laser beam that has interacted with the particle. And if you recover this light, the forward scattered light, for example, and you bring it to a quadrant photodiode, you can track the motion of the particle with respect to the equilibrium position, and you obtain time traces of the X and Y, for example, position like this. What you see here is just that the particle is moving around because of Brownian diffusion, but the average position is kept constant. What you are seeing here is just a voltage signal that is generated by the quadrant photodiode, but you typically can calibrate your system with some very basic models to calibrate this voltage signal into a displacement signal, and from this you can obtain also the forces if you know the stiffness of the trap. We will typically be working with the power spectral density, that is something like the Fourier transform of the trajectory, and it is typically for the case of a Langevin equation described by an overdamp in the overdamped regime. It's a Lorentzian function where you have this characteristic frequency that we call the cutoff frequency, that marks the change of regime where the particle changes from diffusion that you observe at high frequencies to a trap state where you see that the particle cannot diffuse away from a given position, so that the particle is confined to a region, as we see here in the time traces, that is given by the stiffness of the trap. Okay, so that was a brief introduction of the technique. Now I will introduce the outline of my talk. I will not go into too many details. My intention today is to share